I want to motivate this discussion on FlagCalc, the tool for first sort of querying of graphs and for graph research generally, just by showing a sample of the language FlagCalc uses to speak graph theory. That is how we build up a set of vertices and edges between them and that sort of thing. So I'm going to show a couple of screenshots. The first one is going to be a complete graph on n vertices. The next one's going to be a bipartite graph on 3 and 2 vertices, for example, a complete bipartite graph, that is. And lastly, just incidence matrices and how those work. Now, I want to just go right into this now to give this overview. FlagCalc is designed to be a sandbox to encourage novel uses and to be a working apparatus for wielding massive CPU power with the aid of conjecturing and graphing, identifying example graphs through first-order criteria and simply playing around. Many side aspects are worth a YouTube video in their own right. The ability to select a randomizer and code in C++ new randomizers within the object-oriented framework of FlagCalc. The ability to count automorphisms, the ability to sort a database of graphs according to isomorphism class. For example, maybe you want a random graph having an average of E edges. Use R1, the default randomizer. If you want random graphs with a fixed edge count, use R2, etc. Always remember that running FlagCalc with the -H option will output a user's guide. And it literally asks each component of the tool to identify itself on screen in that readout. So it is up to date and as well if at times cryptic. But today your presenter, the author of FlagCalc, wishes only to encourage those with a vision to go farther than he has in simple computer-assisted research into pure math. And the emphasis will be on the typed first-order language built into the command line tool for working with a given database of graphs. This is the feature known as -A, check criteria as it's called. We call it check criteria, but we allow criteria, measures, tallies, the first being Boolean, the second being real, the third being integer, and even set type outputs. You can output a set of items recursively understood. That database is called a workspace. What I've been referring to as a database is called a workspace in this tool. And your typed first order statements are called queries. Queries iterate, meaning you call a first subset of the workspace, then further call that one, and so on until all of your prospective theorems hypotheses are met, or until you found the sample graph you were looking for. The workspace is populated either by standard input, by invoking a named randomizer, or by specifying a computer-readable file, which by design is also human-readable. In other words, your workspace can consist of all graphs that were output by a previous invocation of FlagCalc. It can consist of a large file output by, say, a Python script. It can be your own specially coded randomizer within the C++ framework, which, like most of the processing, is multi-threaded. That query is based on that lingua franca of math research called first-order logic, with types and first-order extensions like big cup, big cap for type set using the latex notation, sum, product, mean, min, max, tally, etc. These extend the usual first-order quantifiers for all and exists. The types consist of Boolean, discrete, aka integer, continuous, aka floating point, set, namely of any collection of types understood recursively, tuple, an ordered set, and graph, set of vertices and edges. For example, a basic query identifies those graphs that are one connected, aka connected, and then as a sanity check in iteration 2, identify all that satisfy the condition forest and not tree, well, namely none of them. You can't be a forest if you're connected and not be a tree. Another basic query concerns the average edge count of those graphs randomly obtained on n vertices with edge probability 1/8, which are triangle free, 18.47. Edge count, average edge count, run on 1 million graphs in around 12 seconds on an Intel i7 processor. Then we find that about 11% of 100,000 random graphs each on 18 edges are triangle free. Let's look at it from a different perspective. The power of the querying language is that it can express substantial theorems using features like stored procedures, alongside the keyword quote-unquote naming, which was a big step forward for the code. For stored procedures, this is a term borrowed from SQL. It means you can type up in the first order language little subroutines, or large subroutines. Subroutines certainly can build on each other. One accidental benefit of this design is that you can use a syntax editor like JetBrains, CLion, etc. to match up left and right parentheses properly. In others, that any research outfit can publicize their brand of stored procedures.dat with emphasis on how they are looking at the world these days, or at least how they're querying graphs. The naming keyword allows you to bundle time-expensive tasks like cup, that is set theoretic union, which requires checking that each item occur only once in the final product. Think about it in terms of a set that's recursively consisting of sets, and so there's a lot to check. Into a named variable, which can then be used anywhere inside the scope of the naming. For basic examples of the simple capabilities of the querying language, the shell scripts testsuite.sh, testsuite settheory.sh, and testsuite setops.sh each go in great depth to the power of the language. There's not time here to elaborate on each implication of FlagCalc, except to show a few screenshots and to say that the author hopes these practice shell scripts inspire, encourage collaboration, novel vision, and cutting-edge discoveries.